Is my screen visible?
Yes, sir. Yes, sir.
Okay. So just a minute. So welcome everyone to fifth lecture of fifth TUT of Analog Circuits course. And I hope you guys have gone through the lectures so far. So before I start my own content, do you have any doubt in the lectures that or anything that you have gone through so far, or maybe some assignments or previous assignments?
Sir, actually, in
Yeah, yeah. Tell me. Yeah,
fifth assignment they have given out filters, na sir. In
the
previous filters,
filters.
in
Yeah.
previous assignment they have given about the what we call as our it is related somewhat related to control systems. Now,
Okay. Yeah.
now,
Stability, of course. Yeah. In stability, it will be related to control system.
yes, sir. So now what you have taught is in previous was about filters, na sir. So if it would have been related to that one, it would have been better. My opinion, sir.
Okay. So any specific concept that you couldn't understand in that and you want me to
No, no, no.
cover?
It is okay. I have answered the assignment. There is no problem.
Okay. Okay. Sure. Okay. Okay. I will consider that feedback. Thanks for the feedback. Yeah. So, okay. So, let's start with. So, Subha, you can mute yourself for now so
Okay.
that there is less noise. And if anyone of you have any doubt, you can unmute yourself and let me know. So, okay. So, uh, let's start with today's session. So, in this particular week, we have mostly covered about the feedback systems and everything, and the stability of the feedback systems. We studied basically two compensation techniques of the feedback systems, and what are those compensation techniques? Those compensation techniques were dominant pole compensation and Miller compensation. Now, dominant pole compensation is a fairly easy system. So let's quickly revise both of them. So we will mostly talk about compensation techniques. We will quickly revisit we will revisit both the techniques, the dominant pole and mirror compensation. I will try to provide a little bit of more insight into how the Miller compensation works and what are some more modifications that can be done in Miller compensation in order to make that better. And after that, once we have done that, then we will basically see yet another kind of compensation, that is a feed forward compensation. So let's start with it. So basically, first of all, what exactly, why do we need compensation? Can anyone explain that?
Sir, to make the system stable.
To make the system stable, and why a system becomes unstable. So in the analogy, so how you can see it, if there is a delay between the feedback path in the feedback path, then the system tends to become unstable. And why is it so? It can be easily understood by some one example. Let's consider a feedback system. So the feedback system that we are going to consider is, let's say you are driving a bike. Okay. So there is a speedometer. You have a speedometer that is present in front of you, and you are looking at it. your brain basically is seeing you are seeing this speedometer through your eyes. Okay, and you know that, okay, let's say you want to drive at 50 kilometers per hour, and when you are seeing the speed, then you are pressing the accelerator, and you are getting some speed. Now this speed is again sped to the again is shown by the speedometer, and this loop is formed. Okay, so basically what happens is, so there is some speed with which the vehicle is moving. So let's say 30 kilometers per hour. Now if you see 30 kilo, so let's try to draw that curve. So the first case we assume is that, okay, the speedometer gives the speed without any delay. Okay, whatever speed is there of the actual vehicle, it will give it to you without any delay. Okay, so if that happens, let's say you wanted a speed of 40 kilometers per hour. 40 kilometers per hour was the required speed. Okay, and initially you are at 30 kilometers per hour. Okay, now you see that with your eyes, and what you do, you accelerate the vehicle, and the speedometers, so the speed starts increasing. As the speed starts increasing, so this is speed, and this is, let's say, time. As the speed starts increasing, the speedometer shows the increasing speed. Then you keep on pressing the accelerator till it reaches 40, and then you make the accelerator constant, and you reach 40 kilometer per hour speed. Okay, but now let's say the speedometer had some delay in it. So this is so the black curve over here is no delay in speedometer. Okay, now let's say the speedometer had some delay in it. Okay, so what will happen is, let's say the speed right now is 30 kilometer per hour. Okay, you see at that and start pushing the accelerator. Now the speed starts increasing, but what happens? Whatever speed is there in actual, the speedometer gives that speed after, let's say, 5 seconds. Okay, so what will happen is, whatever you are seeing in the speedometer is the speed that was there 5 seconds before the current time. The speed right now is higher or lower, whatever the case is. So you will see the 5 seconds previous. So as you are pressing accelerator, the speed of the vehicle is constantly increasing, right? Let's say some constant acceleration is there. The speed of the vehicle is constantly increasing, and it has crossed 40 kilometers per hour, but the speedometer is still showing the previous speed, so you don't know that the speed of the vehicle has crossed. So speed of the vehicle would have actually crossed it, but you are still thinking it's less than 40 kilometer per hour. But then suddenly it will start showing that, okay boss, you have crossed 40 kilometer per hour, then you will reduce the speed. So if you reduce the speed, then again the speed will start reducing, but the speedometer will show that reduced speed after some delay. So again it will go down 40 kilometer per hour, and then this cycle will keep on repeating. It might so happen that after some time you will converge at 40 kilometer per hour. Okay, so this is what happens when system has delay. So basically, you don't directly reach to the desired value. You reach to the desired value with some oscillations around the desired value. Now, as the delay keeps on increasing and increasing, this ringing or this oscillation keeps on increasing and increasing. Okay, till the point the delay becomes so high that you basically it just becomes it never settles to the actual value. It just keeps on like oscillating around it, and after some point the system, what do we call unstable system in true senses, that what will start happening is it will start increasing like this. Okay, so instead of converging, it starts oscillating around the desired speed, but it starts basically the oscillations keep on increasing, and then the system becomes unstable. So as the delay is added to the system tends towards instability. Now, what happens when poles are added to the system? Poles can also be considered as delay. Okay. So what happens basically? So let's say one pole is added to the system of the value. So this happens. So this example was a generic example. Now, as far as circuits are considered, we will consider poles and zeros. So let's say one pole is added to the system, A upon 1 plus S by P1. Okay. Now, if this pole is there, this basically what it will give you is the phase. So let's say, just a minute. So you know that e to the power minus std is basically the delay in Laplace transform, right? So this can be approximated using Taylor series approximation as 1 minus std. Okay. And again with binomial expression, this can again be approximated as 1 upon 1 plus std. Correct? So basically, a pole in the system also acts as a delay. And in intuitive things, how you can see is, so how a pole is added to the system? The pole is added, let's say, because of a capacitor. Okay. Now, if there is capacitance in the system, what will happen is there will, so let's say there is capacitance at some node. Okay. Now, in order to charge this capacitance to a certain value, some time will be taken, right? If there was no capacitance, the value of this node can change instantaneously. But if there is capacitance, some time will it will take some time to change the value of the capacitance. So basically, adding capacitance is equivalent to adding poles is equivalent to adding delay in the system. So basically, this is what. So if more and more poles are there in the system, your system becomes more and more unstable. Now, how the stability of a system is quantified? So this is an high-level explanation of what how delay makes the system unstable and how a pole adds to the delay in the system. But how it is actually quantified is so quantification of quantification of stability. So, can any one of you tell what parameters we use to quantify the stability of a circuital system or a control system? Okay, so basically what we do is, so we have a negative feedback system, and mind it, only negative feedback systems are stable. Positive feedback systems are not stable. Okay, so we have a negative feedback system. Now, let's assume that the forward transfer function has some frequency dependence. It has some amount of poles, and it passes through a feedback factor. So this is your negative feedback system. Now, what happens is if you try to plot its open loop transfer function, it will look something like this. So at the DC, the gain will be some very high value. Let's call this G0. And then the first pole will come. Let's call this P1. So after that, what is the roll off that you will see? So in Bode plot, what is the roll off that you see after a single pole system? After the 1st pole has hit? Guys, if you answer, it will be easy for me to understand that, okay, people are at least listening. Or are you following the discussions?
Sir, I am in the class, but I have not gone through the videos. Sincerely saying.
Okay, so you know about Bode plot, right?
Yes, sir. Yes, sir.
Yeah, so a single pole system with what rate does after the first pole hits, with what rate does the Bode plot falls?
Minus 20 decibels per decade, sir.
Correct. So after the first plot, this will fall by minus 20 dB per decade. Okay, and then the second pole will hit, it will become minus 40 dB per decade. Okay, so this is its magnitude response. How will its phase response look? Its phase response will again start from, so we are plotting the magnitude and phase response of g times beta, and not the so in actual, the if you see, the loop gain will be will have this 180-degree phase shift also, but we are for now plotting the magnitude and phase response of g times beta. So it will start from 0 degrees at the first pole. It will, so let's consider three poles over here. So this is minus 40 dB per decade, and this is minus 60 dB per decade. Okay, so as it starts, so phase margin will look something like this. At the first pole, it will come. So let's assume all the poles are very far apart. So with the first pole, what will happen is it will go till minus 45 degrees, and it will get settled at minus 90 degrees. After the second pole, again it will fall to minus 135 degrees and settle at minus 180 degrees. And at the third pole, it will go to minus 225 degrees and settle at minus 270 degrees. Now the problem will happen is, if so what will happen is, if let's say this g times beta, when the phase becomes more than 180 degrees, so when the phase crosses 180 degrees, what happens is, so if the phase is 180 degrees and this we get another negative 180 degrees from this negative phase shift. So at this point, when the phase of g times beta becomes 180 degrees and we get more 180 degrees from the negative feedback, the overall feedback has a phase of 360 degrees. That means to say that the system has now come into positive feedback at that frequency. Now, if the system is at positive feedback, then it might so happen that the system will start oscillating. The system can become unstable. Positive feedback is always unstable, right? So, what we must make sure is, at the time when the system is going into positive feedback, the gain, the overall loop gain of the system must be less than 1. So, it must be less than unity. And if that is made sure, then basically we can say that the system is stable. What will happen if it is less than unity? So let's say there is some disturbance at the frequency at which the phase is becoming 180 degrees. So as that disturbance will move through this complete loop, that disturbance will die down because the overall loop gain is less than 1. So that won't cause any trouble. But let's say if the disturbance was greater than 180 degree, if the loop gain was greater than 180 degrees, so as the disturbance flows across the loop, the disturbance amplitude will keep on amplifying and the system will become unstable. Okay. So what do we need? That at the frequency at which this 180 degrees crossed, we need the gain to be less than unity, and how much ever the gain is less than unity is called your gain margin. So, okay, if I will push this axis a little up so that the gain margin is clear. So, this is your gain margin. So what does gain margin means? That the amount of margin that you have till the time you can increase the gain of the loop till so if you can increase the gain of the loop by gain margin times, and a system can still be stable. If you increase the gain beyond the gain margin, the system will become unstable, because at 180 degrees the system will have a gain greater than 1. Okay. Other way to look at it is, so let's say my gain has become less than unity at a frequency of at certain frequency. What I can see is my what I should make sure is my phase should be less than 180 degrees, so that like at this particular point my system shouldn't become unstable. And how we measure that is by phase margin, that I can provide additional phase lag of phase margin before the system becomes unstable. Okay, so so these two concepts actually quantify the stability of a particular system. Now let's see, how do we say the system is unstable and how do we compensate it. So let's say if we had a first order system. First order system. Okay. So first order system, can please someone from the students please help me draw the Bode plot of a first order system. How will the magnitude response look? Let's say I have g of 0 over here. How will the magnitude response look? It will start with some it will be flat for some time. After that, the first pole will hit. This is P1, and then it will start dropping with minus 20 dB per decade. Okay. Now, how will the phase response look? It will start with 0 degrees. It will go to minus 45 degrees at the pole's location, and then will settle to minus 90 degrees as the frequency becomes infinite. So now you can see that this system can never become unstable. Okay. How I am saying that is, no matter what happens, no matter how much delay you give, maximum phase that the complete loop can give you is 90 degrees. Okay. And like at all cost, the worst case phase margin that you can get from a first order system is only 90 degrees, because we have to see how much it is above minus 180 degrees, right? So in the worst case, even if the no, even if this zero crossover frequency happens at a very high frequency, still you can't go, the phase margin can't go below 90 degrees. Hence, our system will always be stable. But what is the problem with a first order system? So, what happens is, so let's say you are trying to build an amplifier. So what you will have is you will have A upon A by S, A upon 1 plus S by P1. Okay. Now let's say this gain is not enough. So you will build a second, you will put a second system in cascade. So let's say this is by P2. Okay. So this will now become a second order system. Now in second order system, what will happen? My I will try to plot the Bode plot of this. So now G of 0 is equal to A square. Earlier it was, so let's say here the system was A upon 1 plus S by P1. So here it was only equal to A. My DC gain has definitely increased. So this is A squared over here. Here it will come as P1. Here it will come as P2. And then it will fall below 0 dB at some particular frequency. And how will my phase response look? It will start from 0, come at minus 45 degrees, and then again it will come at minus 135 degrees at the second pole, and then settle to minus 180 degrees. So what happens here? Here also the phase crossover frequency will never come. So the phase will never cross 180 degrees. So you can say that okay, the system will always remain stable. That's correct. But the stability, like it is not only necessary for the system to go in complete instability, and then only you will say that the system is unusable. Even if the system has poor stability, so how the stability is quantified is by a phase margin, right? Because here no gain margin will occur, because the gain can never go. So because since the phase can never cross minus 180 degrees, so there is no point in discussing phase margin. Sorry, gain margin. Only thing that we can discuss is the phase margin. Now phase margin in worst case can go to 0. So we can say that okay, the system is at least marginally stable, but that system won't be practically usable. For example, right, the as I discussed the accelerator example. Now, let's say the system had a 180-degree phase shift and the system was marginally stable. What will keep on happening? It will never give you, you would never go at a constant speed of 40 kilometer per hour. You will keep on oscillating between a very high speed and very low speed, which is again impractical thing. Or let's say you are operating, you are having an air conditioner. You want the temperature set to be at, let's say, 25 degrees Celsius. Now if the system is marginally stable, what will happen, the average temperature will always remain 25 degrees Celsius, but AC will keep on going from let's say 18 degrees to 30, all the way up to 30 degrees, and keep on oscillating. You will never hit a proper 25 degrees Celsius. So even a marginally stable system or a poorly stable system is impractical. What we want is the amount of stability. So typically, what happens is a system with around 60-degree phase margin is considered to be stable enough. What will happen if I try to make the stability too high, and the system will become slow, the bandwidth of the system will reduce. So let's say if in order to increase the stability, I can make the system very slow, then also it's not very practical, because let's say the 25 degrees Celsius I want will reach in 2 hours, let's say, from the AC, and that is also not practical, right? So there is the 60-degree phase margin is generally considered a good trade-off between the speed of the system and the stability of the system. Okay. So we will try to see how. Right now you can see the phase margins is only is almost zero, right? So what we do is, so stability techniques. So how do we make the system stable is, so let's try to first of all visualize this circuit. So this has been done in the course, so you can go through that also. So how generally this circuit is visualized is, so in the previous lecture, in the previous tutorial, you might be aware that I introduced a transconductor, right? So this system can be visualized as follows. So we have an input with some GM1. Let's say this is R1, and some capacitor is there at this node. Let's call this C1. Okay. Now there is some other next stage of this that has GM2, R2, and C2. Okay. So what is my V out by V in? My V out by V in comes out to be GM1 R1, GM2 R2 divided by 1 plus SC1 R1 times 1 plus SC2 R2. Okay. So this is my V out by V in. Now, can anyone help me write the phase of this particular expression? So let's call the, so wherever the gain crosses, gain hits 0 dB, this is called unity gain bandwidth. Gain bandwidth. Okay. So how do you write so right now you see that unity gain bandwidth is at a very high frequency till the time this phase basically hits 180 degrees. Now, what happens if I push this pole? So what I will do in dominant pole compensation. So currently we are discussing a stability technique called dominant pole compensation. So what happens here is, so we saw that a first order system is always stable, right? We see over here that in first order system, the phase margin can never go beyond 90 degrees. Below 90 degrees, so it's always stable. Now, how do you? So what we will try to do is we will try to somehow make any system that we have uh, approximately equal to a first order system. Okay. So how it can be done is, if we keep on moving this pole towards left, what will happen is, so let's say this pole has been moved to PCOM. Okay. So now what will happen is, let's say it is this thing. Okay. So what happens is the second pole hits after the gain has already reduced below 0 dB, right? So if this is the scenario, then we will say that okay, our system has now become approximately equal to first order, and our phase margin of the system will improve. So let's say and how do we get this P-comp? This P-comp is achieved by adding a capacitance of value C comp with the pole that is nearest to the origin. So let's say my first pole was nearest to the origin, R1 C1. So I add a additional capacitance at this node, and what does it do? It basically pushes the pole from P1 to P comp and make the system look like approximately a first order system. But what is the drawback of this? So there are two drawbacks. You will need a very high value of C comp. So you will need a very huge capacitance. Okay. In order to push the pole from P1 to a very low value, the amount of capacitance that you will be needing is a very high capacitance. Okay. And other thing is that pushing this pole to a very low value will make the system also very slow. Okay, the bandwidth of the system will reduce. So, though both the problems actually occur when you do dominant pole compensation. This kind of compensation is a good compensation technique for the systems with, let's say, the DC systems. For example, you need a voltage regulator. A voltage regulator need to provide DC voltage. There also you need transient improvement and all, but like okay, anywhere or the precision ADCs, or where you don't care too much about the speed, but you care more about precision. So there you can use these kind of compensation. But anywhere where you need high speed, there this kind of compensation won't actually work. So there is another kind of compensation that is called Miller compensation, and this also has been taught in the class. We will try to actually gain some more insight in the Miller compensation and see how does it actually works, and what further modifications can be done in order to improve that. Okay. So what happens over here is, so we need a very high value of capacitance looking in from this node, right? Now, how this high value of capacitance can be achieved is, so you guys have studied about Miller effect, right? What is the Miller effect? Can anyone explain that? The Miller effect was taught in, I think, second or third week. So I hope you guys know about the Miller effect, right? Okay, I will quickly go through that. So you needed a value of capacitance, let's say C comp over here. Okay, now the capacitance value is very large in actual. So what I am trying to say is, so let's say there is a capacitance connected to ground. The looking in capacitance from here will be C, right? And how do you define the C as? Q by the voltage. Okay, so Q equal to CV, correct? So what happens is that for a certain charge that you pump into the system, the voltage will increase by some particular value. Okay, so so let's say this. So if 1 coulomb of charge is pumped into this capacitance, the voltage across this capacitance will increase by C volts. Okay, this is how a capacitance can be visualized. Now, if I want to increase this C, basically what I am saying is, for 1 coulomb of charge, now the voltage will increase by a lesser value. Correct? Sorry. I is equal to C dV by dt, right? Mm, so Q is equal to CV. Correct. So what basically I'm going to do is, so let's say there is some voltage that is applied over here. Okay, if this is connected to ground, then what will happen is the the overall voltage across this capacitance will only remain as V. Now, if I have a negative amplification of value A, and instead of connected it to ground, I connect it to, let's say, the lower plate of the capacitance. So the voltage across the effective voltage across the capacitance now becomes, now this voltage will be AV, right? And if this voltage is AV, the overall overall voltage across this capacitance becomes 1 plus AV. Okay. Now, the so let's say the charge pumped in over here is still Q. So what we will get is, for same charge pumped in, the overall voltage across this capacitance is effectively becoming 1 plus AV, right? So is equal to Q, correct? So I am pushing some charge on this top plate of the capacitor. The overall voltage that is being developed across this capacitance, instead of C, it is becoming 1 plus AV times C. Now at this node, the voltage still remains V. It is not becoming 1 plus A times V. So it can be visualized as some voltage V is applied over here and some charge Q is developed at the top plate of this capacitance. But so the effective capacitance that we are looking at is 1 plus A times C. So this is basically mirror effect. Okay, Miller effect. Now what happens is, how do we achieve Miller effect in this particular scenario is as follows. So let's say this particular transconductor had a negative transconductance of value. So this transconductor had a negative transconductance of value minus GM2, right? So the gain from V1 to V out, the DC gain will be minus GM2 R2. So this particular configuration over here of this combination of resistor and transconductance can act as a high negative gain. And if we connect the capacitance like this over here, it basically gives us the looking in capacitance from here becomes Cc times 1 plus Gm2 R2, and hence instead of having the value of C compensation, now you can have a value that is much lesser than C compensation, thanks to the negative gain that thanks to the Miller effect that is happening due to the negative gain with across the second stage. Okay. So now let's try to figure out what is the transfer function from input to output in this. So V naught by Vi we want to find out, right? So it's a rigorous derivation. Let's try to do that, and once we have done that, we will try to figure out what all insights we can get through that derivation. So let's first of all write KCL at V1. So this current is basically Gm times Vi, and how we'll write it as V1 times 1 by R1 plus SC1 minus, sorry, plus V1 minus V naught times SCC is equal to Gm times Vi, correct? So let's try to reorganize this. So we have V1 times 1 by R1 plus SC1 plus CC plus, sorry, minus V naught times SCC is equal to Gm times Vi, correct? Yeah. So this is KCL at node V1. So we can do the same thing at output node. So what we get is V naught times 1 by R2 plus SC2 plus V naught minus V1 times SCC is equal to minus Gm times V1. Okay. So we can again reorganize the terms. So V naught times 1 by R2 plus S C2 plus CC minus V1 times S or plus V1 times Gm minus SCC is equal to 0. Okay, so these two equations we have over here. So let's try to solve these two equations. So what we need is we need a relation between V naught and Vi, right? So we need to eliminate the term of V1. So in the first term, if we divide the complete equation 1 by the coefficient of V1, we get, what do we get? V1 plus, sorry, minus V naught times SCC one plus S C1 R1 plus CC R1, and this R1 will come over here is equal to, this is GM1, this is GM2. Okay, GM1 R1 times VI divided by S C1 plus CC times R1. Okay, so here also I can write it the same way, C plus C1 times R1. Okay, so this is the first equation. The second equation, from the second equation, what we'll get? So V naught times 1 plus S R2 times C2 plus CC divided by, this is equation 3, GM2 R2 1 minus SCC by GM2 plus V1 is equal to 0. So what I have done is, I have divided the second equation completely by the coefficients of V1, and in the coefficient of V1 I have taken out GM2 common. So when I take out GM2 common, the denominator of V naught will have GM2 R2, and with SCC it will get divided down by GM2. Okay, so with the two equations we have, equation 3 and equation 4. So we can do equation 4 minus equation 3. What do we get then? So V1 and V1 will be cancelled, and we get here as 1 plus S R2 C2 plus CC divided by GM2 R2 1 minus SCC by GM2 plus SCC R1 divided by 1 plus SCC plus C1 times R1 is equal to minus GM1 R1 VI divided by 1 plus SC1 plus CC times R1. So simplifying this, what do we get? So like taking the LCM will be basically product of the two denominator. So what do we get over here? 1 plus S R2 times C2 plus CC times 1 plus SCC plus C1 times R1 plus SCC R1 GM2 R2 into 1 minus Mhm. SCC by GM2. SCCR1, GM2 R2. Yeah. Okay. So this is what we have, and at the bottom we will have as GM2 R2 1 minus SCC by GM2 times 1 plus SCC plus C1 times R1 is equal to minus GM1 R1 VI divided by 1 plus SC1 plus CC times R1. Okay, now these two terms can be cancelled, and what we have over here, V naught by Vi is equal to minus GM1 R1 GM2 R2 into 1 minus SCC by GM2 divided by, so we will try to simplify this. So with S square terms, S square, what all we will get over here is R1 R2 uh, C1 plus CC times C2 plus CC. Correct? Okay. So this is the term we'll get with S square, and what terms we'll get with S? With S, we get over here is CC, and with S square we get one more term from this particular this term also, and that is minus CC square R1 R2. Correct? So if we simplify this, okay, we'll simplify it later. First, let's write all the coefficients and then we will worry about simplification. So with S, we get CC R1 GM2 R2 plus C2 R2 times C2 plus CC plus R1 times C1 plus CC. And the last term is 1. Okay. So this is the equation. The best simplification we can do for this is GM1 R1 GM2 R2. So if we open this term, what all terms we will get? We will get C1 C2 CC C2 CC C1 and CC square. So CC square will get cancelled with this CC squared. So what we get finally is R1 R2 times C1 C2 plus C2 CC plus CC C1, and CC squared gets cancelled out, plus S times CC R1 R1 times uh, GM2 R2 CC plus, sorry, 1 plus GM2 R2 times CC plus C1 plus R2 times C2 plus CC. So this is the second term, right? Uh, have I missed something over here? R1 goes with this. Yeah, plus 1. Okay, and now you can see this is a polynomial in second order, right? So it will. So overall, we can comment. What we can comment on this system is that the system has one zero that is on the right half plane, and the system has two poles inside that. Okay. So the zero is very clear from this particular equation. So where does the zero exist? The zero exists at. So there is an zero over here that exists at GM2 by CC and RHP 0, the right half plane 0. Okay, sorry, RHP 0. Now, what are the two poles? So, looking at this expression bluntly, the finding out poles or getting any insight on what the poles are is quite impossible. So, what we will assume is, so we will make some assumptions, and based on that, we will try to approximate the poles. And so, how do we go about making the assumption? So, the very reason that we went for this Miller compensation was we wanted the inside pole to be at a very low frequency. So, basically, what we wanted was we wanted that both the poles should be very far apart, right? So that till the time the second pole hits, the gain of the system has already gone below 0 dB, and the second pole is insignificant. So uh, if this technique is effective, that means to say the two poles that are there in the system will be very far apart, right? Now, if that is considered, we can apply some basic approximations. So let's try to see what is a generic second order system. Order polynomial. So it looks like ax square plus bx plus c is equal to 0. Okay. Now, what are the poles? So let's say what are the zeros of this particular? So the poles that I'm talking about are actually zeros of the denominator, right? So what is the zero of this particular polynomial? So let's say the zeros of this particular polynomial are P1 and P2, or okay, let's call them Z1 and Z2. So these are the solutions for this particular polynomial, right? So so what we know from our high school mathematics is that Z1 plus Z2 is equal to minus B by A, and Z1 Z2 is equal to C by A. This is clear to you? Now, if let's say these two solutions are very far apart. So one solution is very small, other solution is very large. So what will happen? So let's say Z2 is much greater than Z1. So this particular equation can be approximately so Z1 plus Z2 will all approximately be equal to Z2 only, right? Because Z2 is much greater than Z1, so Z1 in the summation can be neglected. So Z2 can approximately be written as minus B by A, and Z1 how it can be written? Since Z1 Z2 is equal to C by A, so Z1 will become and since Z2 is approximately minus B by A, so Z1 will become C by B minus C by B. So if the poles are far apart, if the poles of a polynomial are far apart, what we can say is the poles can approximately be written as, so the dominant one, larger, the pole at larger frequency or the non-dominant pole will be equal to minus B by A, and the other pole will be equal to minus C by B. Okay. So the same thing we will apply over here. So we have this equation present to us. Now we can what we can write it as. So our one pole can be approximated as minus B by A, right? So this is our B term, this is our A term, and this is our C. Okay. So omega P1 can be written as minus of R1 times 1 plus GM2 R2 times CC plus C1 plus R2 times C2 plus CC divided by R1 R2 times C1 C2 plus C2 CC plus C1 CC. Okay. So how this can further be simplified is, now we know that as we said, so let's try to simplify it even further. As we said initially that our this transconductor, this transconductor and resistor pair form a very high negative gain in order to give you the true benefit of Miller compensation, right? So if this is a very high negative gain, so GM2R2 is going to be a very high number, right? Very huge number. So one can be neglected in comparison to GM2R2. So this basically becomes minus R1 times GM2 R2 CC plus C1 plus R2 times C2 plus CC divided by R1 R2 C1 C2 plus C2 CC plus C1 CC. Okay. Now other approximation that can be made is for as follows. So what we have over here again is that this R2 over here is also a very small quantity, correct? Now this R2 times C2 plus CC will be much smaller than this GM2 R2 times R1 times CC, right? So all the terms except this particular term can be neglected from the equation. So what we can write over here is minus GM1, GM2, R1, R2, CC divided by C1, C2 plus C2, CC plus C1, CC. So this can further be written as follows: minus GM, sorry, there is no GM1 over here, minus GM2, and R1, R2 is also gone. This is basically, so this R1, R2 cancels the top one R1, R2. So what we have over here is GM2 CC upon C1 plus C2 divided by 1 plus, sorry, uh, CC plus C1 plus CC, and this can be written as C2 plus C1 CC upon C1 plus CC. So it's the same thing. Whatever is written over here, the same thing I have manipulated and written in this format. So you can just do the math and get to this. So basically, what I have done, I have taken C2 common from first two terms, so it becomes C2 times C1 plus CC, and then I have taken C1 plus CC common from this complete denominator and put it outside. So it becomes C2 plus C1 CC upon C1 plus CC. Now, why I have written it in this manner? So our pole, as you can see, is now GM2 times CC divided by C1 plus CC into C2 plus C1 CC upon C1 plus CC. Okay, we will in few moments we will try to figure out why do we get this kind of pole. Okay, so let's keep this pole aside for some time and get to omega P2 first. So what was our omega P2, or omega P2, or the smaller pole, or the pole that is closer to the origin, was minus C by B, right? So C is unity, and what is B? The B is written over here. So omega P2 can approximately be written as minus 1 by B. Now what is B? R1 times 1 plus GM2 R2 times Cc plus C1 plus R2 times C2 plus Cc. Okay. Now using the same set of approximations that we made while calculating omega P1, the final value, so in the final expression, only GM2 R2 times Cc times R1 will dominate. Apart from that, all the terms can be neglected. So this just becomes minus 1 by GM2 R2 CC times R1. Okay. So our system has one right half plane 0 and two left half plane poles. Okay. Now let's try to figure out intuitively how these poles and 0 come about. So let's redraw the circuit over here. So what we have over here is, so first of all, let's figure out omega P1. What was our omega P1? Let's first figure out omega P2. So our omega P2 is approximately 1 by GM2 R2 CC times R1. So how do we get this particular expression over here? So the omega P1, omega P2, I have interchanged the notation, so don't mind it. So omega P2 comes because of this particular node. Okay. Now at this node, what is the equivalent capacitance that we see? The equivalent capacitance that we see at this node is, so looking in capacitance, C equivalent is C1 plus the capacitance looking in into the Miller compensation capacitance. Okay, so the looking in capacitance due to Miller compensation becomes GM2 R2 times CC, right? So equivalent capacitance is C1 plus GM2 R2 times CC, correct? Now, since GM2R2 is a very big number, so C1 can be neglected in comparison to GM2R2 times CC. So equivalent capacitance becomes only GM2R2 times CC. And what is the equivalent resistance from this node? Only R1, right? Equal to R1, correct? So what is omega P2? That is equal to the equivalent resistance multiplied by the equivalent capacitance at that node, which comes out to be minus of R1 times GM2 R2 times CC. The same thing, right? So whatever we arrived at with rigorous derivation and huge amount of approximations can be intuitively also seen that it is correct, right? It's only minus R1 times it's only minus 1 by R equivalent times C equivalent. Now let's move on to the second pole. I'll again redraw the circuit over there. So the second pole occurs at the output node, that we called in our notation as omega P1. So where does the second pole occurs? The second pole, again, we will have to find out the equivalent capacitance and equivalent resistance. So first of all, let's see what is the equivalent capacitance. So equivalent capacitance is, so what will happen is we have assumed that the poles are very far apart, right? So poles being very far apart, what does that mean? That till the time the second pole is hitting, so this pole will be the dominant one, and this pole will be the non-dominant one. Now, what will happen at the frequencies where this pole will start hitting? This pole would have hit long back, right? So once the pole has been hit at this particular frequency, only the admittance, the parallel resistance that is there due to R1 will become much larger than the impedance that comes due to this capacitance C1. So their parallel combination will almost be equivalent to only the capacitance. Since R1, since the value of admittance of this capacitance has become very small in this parallel capacitance, so overall admittance will also be dominated by only the capacitance. So how it can be seen as, so this R1 can be neglected. We have a C1 over here, a GM2 like this, a CC, and C2. Okay. So this is how the system can be visualized. Now, what is the equivalent capacitance? It's basically the parallel combination of C1 and CC, the series combination of C1 and CC in parallel to C2. So what do we have over here? We have C1 Cc upon C1 plus Cc plus C2. Correct? Now, now how do we find equivalent resistance? That's a little bit more tricky. So we have a resistance over here also. So how do you find equivalent resistance? So resistance in any node can be found out by putting in some voltage and checking how much current is being drawn from that voltage. Okay. So we have something like this. R2 Cc, and let's apply a voltage V test over here. Now we will see how much DC current is being drawn by this drawn from this particular V test, and that DC current will give us the value of the equivalent resistance at that node. Now, if we are talking about DC current, so this capacitance will be open circuit. So this capacitance need not be present over here. Now, these two capacitance can also be treated as open circuit, but like we can't exactly do that, and the reason I will tell you. So, what these two capacitances are doing, so if a V test is applied at this particular node, what these two capacitances are doing, these two capacitances are making a capacitive division between Cc and C1. So, if this node is Vt, this node's voltage is Vt, the value of a voltage at this node will be a capacitive division between C1 and Cc, and that is equal to Cc divided by C1 plus Cc times Vt. Okay. Now, if this node is equal to Cc divided by C1 plus Cc times Vt, the current that this transconductor will be sinking in will be equal to Gm2 times Cc divided by C1 plus Cc times Vt. Okay. So what happens is, so overall current I test is equal to, so one current will be going in this direction, that is Vt by R2 plus Vt times Gm2 Cc upon C1 plus Cc. Okay. So what is my R equivalent? My R equivalent is equal to Vt by It is equal to 1 upon 1 by R2 plus Gm2 Cc upon C1 plus Cc. Okay, this can be written as R2 divided by 1 plus Gm2 R2 Cc upon C1 plus Cc. Now again, we said that Gm2 R2 is a very huge number, right? Now, if Gm2 R2 is a very large number, so this can so 1 can be neglected in front of that. So we have ultimately what, R2 divided by Gm2 R2 Cc divided by C1 plus Cc. So R2 gets cancelled, and our R equivalent is equal to 1 by Gm2 times Cc by C1 plus Cc. Okay. So again, what is our second pole? Omega P1 is equal to 1 by, again, R equivalent times C equivalent. That is equal to, what was our C equivalent? C2 plus C1 Cc upon C1 plus Cc, and since it is 1 by this thing, so 1 by R equivalent will be reciprocal of this. So it can be written as Gm2 Cc divided by C1 plus Cc. Okay. Now this is our second pole. So as we see, whatever we derived, so this is what we derived, right? Now you can see that whatever we derived from a mathematical expression, the same thing we got by the set of approximations we did for our circuit. Correct? So what happens is, now if this capacitance, if let's say this capacitance was not there, then what would have happened? Our so if let's say we had only so uncompensated circuit looked as follows. R2, C2. This is GM2. So what would the pole be? Omega P1 would be 1 by R1 C1, and omega P2 will be 1 by R2 C2. Okay. If the Miller capacitor was not there. If the Miller capacitor is there, so this is without Miller capacitor. With Miller cap, what happens? Our omega P1 was 1 by GM2 R2 CC times R1, and our omega P2 is GM2 times Cc upon C1 plus Cc divided by C2 plus Cc C1 upon C1 plus Cc. Okay. So what is happening is, so initially omega P1 was 1 upon R1 C1, but now it has become GM2 R2 times Cc times R1. Now this GM2 R2 again is a very large number, right? So whatever omega P1 was initially, the omega P1 after Miller compensation has moved inside. So yeah, Suvarao, do you have any doubt?
No, no, sir. The value has reduced. That's what.
Yeah, the value has reduced, correct?
Yes.
So initially it was, let's say, 1 by R1 C1. So now after the Miller compensation, it has become 1 by GM2 R2 CC times R1. Okay. Now, what about omega P2? Initially, it was, let's say, 1 by R2 C2. After the Miller compensation, it has become GM2, this complex, this expression, right? So if you only look at the equivalent resistance, so equivalent resistance initially was R2, and now it is proportional to 1 by GM2, correct? Now, if we are saying that GM2 R2 was much greater than 1, that means to say R2 was much greater than 1 by GM2, correct? So if this was the case, the equivalent resistance that is there after the Miller compensation has reduced significantly. Now if that has happened, that means to say the pole has moved to a very high value than it was earlier. So this pole will be at Cc by C1 plus Cc, GM2 divided by C2 plus C1 Cc by C1 plus Cc. So what do we see in this kind of compensation is pole splitting. The dominant pole moves closer and the non-dominant pole moves even farther. Okay. So this is what pole splitting is. Now what we get from yeah.
Sir, how we get that GM to R2 is greater than 1, that condition, sir?
We said initially, so this was defined very in the very starting moment, right? What do we want from this particular circuit? We want a very high gain, right? And how do we get high gain? We get high gain by cascading these transconductor resistor pair. So from first stage, we get GM1 R1 gain. From the second pair, we get GM2 R2 gain. Now, both GM1 R1 and GM2 R2 should be very large in order to supply a very high. Otherwise, your loop gain won't be very high, right?
Sir.
Do you understand?
Yes.
Yeah. So that's what. So this is how the pole splitting works. What was happening in dominant pole, we wanted a very large value of capacitance in order to reduce, in order to in order to reduce the dominant pole to a very low value. But here that is achieved by a much smaller capacitance. And other benefit that we get is since the non-dominant pole is also moving farther apart. So, in order to get the same margin, the dominant pole should not move that much far apart as it was supposed to in dominant pole compensation. So, the bandwidth reduction will definitely happen in case of Miller compensation also, but the amount of bandwidth reduction will be much smaller than what we had for dominant pole compensation. Now, apart from these two poles, we also saw that there was a zero in the system, right? So let's try to make sense of the zero as well. R1, C1, this is CC, this is GM2, R2, and this is C2. So we want to find the frequency at which the zero of the system occurs, right? Or the value of S at which the zero of the system occurs. Now, wherever the zero of the system occurs, what exactly happens? So the output voltage. So let's say I am giving some input voltage as S. Okay. So if this particular S is the system is excited by this particular voltage, the output has to go to some S naught. Okay, or S0. So our output has to go to zero at that particular value of S. Minded, this is not the frequency. This is the complex input that we are giving. So S is what is it equal to? Sigma plus j omega, right? So I am not considering sigma equal to zero and giving some frequency. I am giving a complex input only and I am calling it as S0. Okay. So at that particular at that for that particular input, my output has to be zero. Now, if my output is zero, and these resistor and capacitor are connected to ground only, right? So no current will flow in this direction. If no current flows in this direction, and let's what will be the voltage at this particular node? Let's call this V1. If this voltage is V1, and the current that will be flowing from here is GM2 times V1. If GM2 and the current that will be flowing in this direction will be, since this node is zero, the current will be V1 times SCC. Okay. So what do we have? Since no current can flow in this particular direction, so all the current, whatever is coming from here, has to flow in this direction only. So V1 times SCC has to be equal to GM2 times V1. That means to say, or SZCC has to be equal to GM2 times V1. So SZ is equal to GM2 by CC. This is the frequency at which, this is the input at which the zero occurs. And the same thing we calculated here, right? So if we look at the transfer function once again, the zero occurs as S equal to GM2 by CC. Okay. So we have figured out what the poles and zeros of this system are. Now let's see what the phase margin of the system is. So the whole idea behind doing this compensation was to increase the phase margin or to increase the stability. Now let's see how much it has increased by, or what is the phase margin of the system. So let's try to write the complete thing once again. So in the transfer, so now I will only write the approximate transfer function. I won't write the exact transfer function. So approximate transfer function is G minus GM1 R1 GM2 R2 times 1 plus SCC by GM2 divided by 1 plus S by omega P1 into 1 plus S by omega P2. Now we can also substitute both omega P1 and omega P2. So what is our omega P1? Omega P1 is GM2 R2 CC times R1. So let's substitute it over here. GM2 R2 CC times R1, and the other one is C2 plus CC C1 by C1 plus CC times C1 plus CC divided by GM2 CC. Okay. So how will the Bode plot of this thing looks like? So we will have some flat response, that, and what is the flat response? GM1 R1, GM2 R2. And after that, after omega P1, it will start falling. And then omega P2 will come. It will start falling like this. And then omega Z will come. It will again become minus 20 dB per decade. Okay, so this is how our system will look. Now, what happens is, so let's say this is our omega UGB. Now till the omega UGB has hit us, only the first pole is dominant, right? So if the first pole is dominant, so in this region, the above transfer function can be approximated as minus GM1 R1 GM2 R2 divided by S GM2 R2 CC times R1. Okay, so this is equal to, the second pole and the zero can be neglected as those are at very high frequencies, and this one can be neglected as this omega p1 has already hit. Okay, so this is equal to, so gm, all these terms get cancelled out. Gm1 times SCC. Now, omega UGB is basically the frequency at the gain at which the gain becomes 0 dB, or in linear scale unity. So that omega UGB comes out to be GM1 by CC. So this is an important expression that you guys need to remember, so that this actually helps a lot while designing the system. Now we know the omega UGB. Now what we need is, we need to see how much phase margin we have, right? So what is phase margin? The difference between the actual phase of the system minus the 180 degrees, minus the difference between the actual phase of the system. So what is this thing? So 180 degrees is basically pi minus the phase of the system. The phase of the system will can be given as minus tan inverse omega UGB by omega P1 minus tan inverse omega UGB by omega P2 minus tan inverse omega UGB by omega Z. So this is basically the phase margin that we'll get. Now we can always go and substitute omega UGB, omega P, omega Z in this equation and get the phase margin. And we have the approximate values of all the system. Now one problem that we see over here is, what we see is that this zero, this is a left right half plane zero. What this zero is doing, like had it been a left half plane zero, then instead of minus, we would have had plus over here, because this will contribute as a positive phase, and this would actually be beneficial for us. Why? Because if that will basically reduce the phase lag. But since this is a right half plane zero, instead of adding a positive phase, it is adding a negative phase. So it is contributing to phase lag, and hence is reducing the phase margin. So we will discuss right now a technique with which we can actually eliminate this particular zero, and hence enhance the phase margin of the Miller compensated system even further. So let's try to figure that out. So what we said is, at a frequency of Sz, this particular input became zero. We want that at this particular frequency, the input shouldn't become zero, and it should become zero at, let's say, some other frequency. So what can be done is, so this is my output, right? This is my V out. So what can I do is, I can add a voltage source of Sz of some k times V1 I can add over here. Okay. So if I add this k times V1, now instead of 0, my output will be some k times V1, which is not exactly, which is not actually 0. I have some voltage, and this is what I want at Sz. I don't want a zero output, I want a non-zero output. So a voltage source can be added over here. Now, if this voltage source is added at this point, so what happens is, so let's say there is a system like this. Okay. So there is some voltage K V1 like this, and instead of that, I make the system as follows. Now, since this node is zero, so we don't need to, let's move this at R2 and C2. Okay. Now, this particular system can also be written as like this. So, this network and this network are exactly equivalent to each other. So, this particular voltage source can be pushed into these two branches. And if we do that, what we get? V1 K times V1 CC. This is K times V1. Okay. Now, a voltage source in series with an ideal current source over here. So this is basically a current controlled current voltage controlled current source, right? So current source with in series with voltage source, the voltage source doesn't matter at all. Okay. So no matter what voltage source I put, if this current source is ideal, the same current will flow in this direction. So this particular voltage source is insignificant. So this voltage source can be neglected, and we want some voltage source over here. Now some current is flowing in this direction, right? If some current is flowing in this direction, if and I want a voltage to be developed across this current, I can simply put a resistor. Okay. And that will current flowing through resistor will add some voltage at this particular node, right? So the same thing we have done. Now let's see where the zero of the system lies. This is GM. So now what we get is, so if this is V1, in this particular current is GM times V1, and since this is 0 volt, so this current is SC plus 1 by R times V1, and since this current will be equal to the current going inside the transconductor, so GM is equal to SCC plus 1 by R. That implies SZ. So basically, we are doing all this analysis by giving input as SZ, right? So we have GM minus 1 by R times 1 by CC is our SZ, correct? So now our zero frequency from CC has been from GM by CC has been shifted to GM minus 1 by R by CC, correct? So now if I control this R, I can move the zero at any position I want. If I make R equal to 1 by GM, then my zero will come at infinite frequency. Then what will happen? My zero will just go away. Do you understand? So this particular resistor over here can make my zero go at a very high frequency and not impact. So if basically my zero becomes at a very high frequency, then I won't be impacted by that zero, right? Then this tan inverse omega UGB by omega Z will become very small, and it won't impact my phase margin as much as it was impacting earlier. So if I make R equal to 1 by Gm, the zero can be eliminated, and this R is called zero cancelling resistor. So by adding this resistor in the Miller compensated path, we can actually enhance the phase margin of the Miller compensation. So this was it from my side in today's lecture. Any doubts so far? R parallel C. Wait a second. Is equal to how you write 1 by. Uh, I'm not exactly able to understand what you wanted to ask. Can you unmute yourself and explain this? Explain your doubt.
No, so in starting you told R parallel with capacitor. Here also in the above, R series with capacitor or R parallel with capacitor starting. How you
No,
write that?
uh, in this particular circuit, you are asking.
In starting first, starting you wrote R parallel with this one capacitor C1, R1 C1.
Which one?
Ah, yes, yes, this one R1 C1
Yeah.
V1
Uh,
V.
s- yeah, correct. So, what is the problem in this?
No, how did you write R 1 by R2 plus CSC?
No, I never wrote 1 by R2 plus SC, right?
1 by R1 plus 1 by R1 plus CSC. Without somewhere written.
I never wrote 1 by R1 plus SC. Okay, I will go through the complete derivation once more. Where,
Yes, yes. Little bit up, sir, up, sir, up, sir. Starting.
okay, let's go to the starting. Okay,
Yes,
here.
sir, here.
Yeah. So, what is the current that will be flowing in these two particular nodes? I am writing KCL at this node, right? So KCL at this node will be current in this resistor plus current in this resistor, this capacitor plus the current that is flowing in through the CC is equal to the current that the transconductor is supplying, right? Do you agree?
Yes, sir.
Yeah. So current flowing in this resistor is V1 by R1, right?
Yes,
And the
yes.
current flowing in this capacitor is V1 times SC1, correct? So I have just taken V1 common and written it as follows.
Okay, sir. Okay.
Yeah. Any other doubt?
Sir, why you write 1 plus A, sir?
Sorry.
1 plus A for this one capacitor. After this one, 1 plus A you wrote, sir.
The Miller capacitance you are
Yes, sir.
talking about.
Yes, sir.
Yeah. The theory of Miller capacitance is so if we have a capacitance, if we have a capacitance across a huge negative gain, then the looking in capacitance from this side is 1 plus A times this floating node capacitance. You understand the Miller concept, right?
Yes, sir. It is only A times you see you can take. No?
No, it's the approximate value is a times c. But in actual, if you see, it's you can go through the derivation. In actual, it's 1 plus a times c. But if a is very large, 1 is neglected.
And this is for like common source, common collectors, common source or common drain, something like this.
No. Any so you see, it will be mostly applicable in common source only. Why it will be applicable in common source? Because okay, let me write this. So let's try to draw the both the circuits. So common source will look something like this, right? And let's say there is some CGD over here. And how will common drain look? Like this. So let's say this is some CGS. Okay. Now gain from DC gain from V in to V out in this case will be equal to minus GM times RO, or this resistance R. Okay. Now this is a very high negative resistance, right? So basically this can be equivalently said as minus A with CGD. But in this case, my gain is approximately 1. So this is not a high negative gain, right? So in common drain, this concept won't work, but in common source, this concept will work. And the looking in impedance from input side will be 1 plus GMR times CGD. So it is effective in common source only. In common drain, it's not effective.
Okay, sir. And why you got zero voltage, sir, at the output?
I got at so at the output. So I was calculating the input SZ for which I get. So I was calculating the zero, right? I was
Yes, sir.
trying to figure out what is the zero. So what does the zero means? For a certain value of S, my output shall become zero at that particular value of S, right? So let's call that value as SZ. So when I give input as SZ, my output becomes zero. So and I wanted to calculate that SZ. So the output is considered zero at that uh, particular input. Do you follow?
Yes, sir. Yes.
Any other doubt?
Sir, gain margin.
The gain margin won't exist here, right? Because as we discussed in the initial part, mm, where is the second order system? This is a second order system, right? So second order system has only two poles. Now two poles can only give a phase lag of 180 degrees, right? So for 180 degrees phase lag, the so if that and that also 180 degrees will come at infinite frequency. So it will never cross 180 degrees. Hence, there is no concept of gain margin in this.
So
Only
for
phase
first
margin.
order, for first order,
Yeah.
we should take gain margin.
No, first order, so nothing is there. First order phase margin is for first and second order concept of gain margin does not exist. For only pole systems, for the system that have only poles in them, the concept of gain margin does not exist for first and second order because the phase does not cross only 180 degrees. From third order system onwards, the phase starts crossing 180 degrees, and there actually the concept of gain margin occurs.
But in really, we will use third order, fourth order system, or only all
No, no,
second order.
but the thing is that the dominant, if let's say the system has multiple poles, okay, but what happens, other poles are there due to very small parasitics, okay, and those are at very high frequencies. So even if it is a third order, fourth order, or higher order system, those poles, the additional poles will lie at very high frequencies. So those generally don't matter only. So the system can be modeled by two poles only, the two most dominant poles. And let's say those poles are there, say third, fourth order poles are there, but they will add phase lag at very high frequencies. By the time we go to those frequencies, the gain has already become less than unity. So if the gain is already very less than unity, so concept of gain margin is not very significant over there. So the phase margin would be a much will be a much bigger concern than the gain margin. So we generally look more on the phase margin than the gain margin part. Any other doubt or any other thing that you wanted to you wanted me to explain? No, zeros don't always lag. Zeros, if the zero is a left half plane zero, it will enhance your phase. It will add to the phase. But if the zero is the right half plane zero, then it will add to phase lag. And in Miller compensation, since it's a right half plane zero, that's why it contributes to phase lag. Had it been a left half plane zero, it would have actually been beneficial. So there is one more technique called feed forward zero compensation. There actually we enhance the phase by adding a left half plane zero. We don't have time in this lecture. We will cover that maybe in the next tutorial. Any other doubts? Pole in right generally don't occur. Pole in right means you can't get a pole in right half plane zero. Pole in left actually lags. So I will just tabulate it over here. So phase lag is given by RHP 0 and LHP pole. Okay, and phase advance is given by LHP 0. RHP pole can't actually come with like a combination of resistors and capacitors. So we generally don't talk about RH. So in open loop configuration, RHP pole is not possible. So we don't talk about RHP pole. Any other doubt? So we are seeing stability from open loop only, right? So this complete so whatever we have over here, this complete thing is open loop only. So what happens is like when we close the loop like this, then we actually see that. So if the system is operating in open loop, it will always remain stable. What we are telling is if this particular system is placed in closed loop, then the delay of the system will be so much that it will become unstable. So An open loop system, what we say is we break the loop over here and check the open loop gain to see if the system is stable or not. So we look at the open loop gain to predict whether the closed loop system will be stable or not. That's how it works. Okay, any other doubts? Okay, if there is no other doubt, that was it from today's session. Thank you for attending.
Thank you. Thank you, sir.